In homework 6.3, we're dealing with radical equations and inequalities. Mostly we're dealing with inequalities here. And inequalities are when two things aren't equal to each other. So let's look at some example problems. Here we're trying to graph y is less than or equal to the square root of 2x plus 6 minus 6. And we're going to graph it as if it were equal to it first. And to graph this, we've talked about how we want to factor out the number inside. And this is a tricky one to graph. Let's make sure we know how to do it. Oh, that's wrong. I should have a 3. 2 times x is 2x. 2 times 3 is 6. And so this will have a vertex at -3, -6. And this is a horizontal compression by a factor of 1/2. What that means is the x values only have to be half as big as normal when we do the square roots. So normally we do square root of 1 is 1, but here we'll only have to do square root of, when x is 1/2, 2 times 1/2 will be 1. And so when x is 1/2, 2 times 1/2 is 1, square root of 1 is 1. Next, we would normally do when x is 4, the square root of 4 would be 2. But now we only need to have when x is 2, the y will be 2, because 2 times 2 is 4, square root of 4 is 2. Normally we would have square root of 9, but here we'll only need to do square root of 4. We'll only need x to be 4.5. 1, 2, 3, 4.5. The reason we need x is 4.5 is because 2 times 4.5 will give us 9, and the square root of 9 will be 3. When x is, we can do the square root of 16, but we only need x to be 8. So we'll go over 8. And when x is 8, we'll be doing the square root of 16, which is 4. So here's our graph. And this is y equals square root of 2x plus 3 minus 6. But we're looking for where is y less than or equal to it. Because there's the equal sign, we can connect the line because this is the line where the values will be equal. If it were just a less than sign or a greater than sign, we would use a dotted line to show that the y can't equal those values. But we're also looking for where is y less than these values. And y is less below. And so what we're going to do is we're going to shade in below. And we're going to be very careful to end right here. And the reason we're ending here is because the y is not below this graph because the graph stops existing. These values of x are undefined, and so the y being below an undefined value doesn't make sense. So when we graph y is less than or equal to, we'll be shading where the y is lower than where it would be if it were equal to. So it looks like this. This will, of course, keep being shaded to the right forever, but it will not be shaded to the left. We're going to take this idea of graphing, and we're going to solve x minus 3 squared plus 4. Where is that less than 8? And last class, we talked about how to solve using graphing when we had equalities. Well, here we're looking for where is this less than 8. The idea is very similar. We're going to graph the right side of the equation. Here's where y is equal to 8. Y equals 8 is a horizontal line. And we're going to graph the left side, y equals x minus 3 squared plus 4. So it shifted to the right by 3 and up by 4. So here's our vertex, and it's a quadratic. So 1 squared is 1, 2 squared is 4, 3 squared is 9, and it's symmetric. And if we were saying where are they equal, we would find these two x values. The answers would be x is 1 and x is 5. But we're not looking for where these two are equal. We're looking for where is this one less than 8. So where is this quadratic lower than 8? And we can see that the quadratic is lower than 8 on this part of the graph. When we're solving an equation, we're looking for what x values make this lower than 8. And the x values that make the quadratic lower than 8 are all of the x values between 1 and 5. We have to be careful about this sign. We don't want where it's less than or equal to. We only want when it's less than. And so the answer is going to be when x is between 1 and 5. Or we could write it like this. This is x is on the interval from 1 to 5. And we use parentheses because it's not or equals to at the end. This is not a point 1 comma 5. That's not what we're saying. We're saying x is between 1 and 5. And again, the reason is because when x is between 1 and 5, this quadratic will be lower than 8. So hopefully we can see it visually. Okay, tricky stuff. We're going to be solving this analytically. And the steps are going to be very similar. We are going to start by squaring both sides, just like we did last class. Greater than or equal to 1. We're going to add 1 to both sides. We're going to divide by 2. And remember, if you ever divide by a negative, we would switch the sign, but we didn't have to here. So x is greater than or equal to 1. But we have to be careful because we need to check and see, is that going to make there be any undefined values in here? And the way to do that is we're going to check for a domain restriction. We're going to see, we need the part that's inside the square root to be at least 0, because if this was ever below 0, we would be doing square root of a negative, and that would be imaginary or undefined. And so 2x has got to be greater than 1, and x is greater than or equal to 1/2. This is like a domain restriction. So these are our solutions. We know that x has to be at least 1, and the question is, are any of the values, so like I'm going to draw a number line here. Our solutions are when x is greater than or equal to 1. But we also have this additional domain restriction that says x has to be at least 1/2. And luckily, all of these are to the right of 1/2. And so these are going to be the solutions. We don't have any problem there. We'll see in the next one where it runs into trouble. We're going to solve the exact same thing, but instead of greater than or equal to 1, it's less than 1. So we square both sides. Okay, great. Less than 2. X is less than 1. And so now, when we do our same domain restriction, the inside still needs to be greater than or equal to 0, because if this were ever negative, we would end up with an imaginary number. And so now let's look at a number line of solutions here. So now, here's 0. When x is 1, we're saying the x's have to be to the left of 1. So like 1/2, 0, -1, -5, -10. All these numbers are less than 1. But if the numbers ever go below 1/2, we'll end up with a problem. And so what this looks like is we say when x is greater than or equal to 1/2, x has to be greater than or equal to 1/2. And the only solutions that are less than 1 but greater than or equal to 1/2 are when x is between 1/2 and 1. So the way we write that is we write 1/2 is less than or equal to x is less than 1. And that's just this part right in here. X had to be less than 1, or this inequality wouldn't be true. And x has to be greater than or equal to 1/2, because otherwise we would be doing the square root of a negative. And so we will only have solutions between 1/2 and 1. Similar idea here. Let's look at this. Let's solve. And we're going to divide by -1 here to get rid of the negative in front. When we divide by a -1, this flips the sign. And we're going to square both sides. And so x is greater than or equal to 4. So again, what that looks like on a graph is we're saying all the x values need to be at least 4. Okay. Here, we want to say that x has to be at least 0. Right? Well, this is weird. What's going on here is we said x has to be at least 0, but earlier we said x had to be at least 4. Well, it turns out that when we check this answer, 4, if we check for an extraneous solution, we get negative square root of 4 plus 3. We're going to check and see, does that equal 5? We get -2 plus 3 equals 1, or equals 5. And this isn't true because the left side is equal to 1. And when we get an extraneous solution, there are two possibilities. Either there are going to be all the solutions work or none of the solutions work. And in this case, since they go in the same direction, the answer is actually going to be x is greater than or equal to 0. All values of this square root function will provide values that are less than 5. What's happening is on a graph, there was no intersection. Here's y equals 5. We talked about solving by graphing on the front. Here's negative x plus 3. Looks like this. And they never intersect. And so we checked for an extraneous solution. And what that extraneous solution told us was that they never intersected. And so either this will always be underneath or it will always be on top. And so we have to look for which one it is. And so either there are going to be no solutions, or in this case, everywhere that works for the domain restriction will be the solution to this graph. This is a really tricky concept, and it goes back to what we were doing yesterday, last class, when we talked about extraneous solutions, meaning that these never intersect. And so now we're saying, well, if they don't intersect, either this will always be below or it will never be below. And in this case, since we wanted to know when it was less than or equal to, it's always below. You can check by using a domain, you can check and see that it's true by seeing if they point in the same direction. And if they do, it'll be all solutions from the domain restriction. This x is greater than or equal to 4 won't be part of our solution because the 4 was an extraneous solution. So if you need more help on that, feel free to get help. I don't feel like that explanation was tremendously clear. The last thing, and this is going to be important in 2 years from now, it's a really important solution technique, is we want to know when this quadratic is above 0. And so the way this is going to go is we're going to factor. And we're going to first start by saying, where is this equal to 0? Well, if this was equal to 0, we would know that the solutions would be x is negative 7 and x is 2. But those aren't the solutions to this, because this will make it equal to 0, and that it won't be greater than 0. But our idea here is, in a quadratic, where it crosses 0, where it is 0 are the only places it could cross 0. And so it's the only time it can change from being positive to negative. And so what we're going to look at is we're going to make what's called a sign chart. And we're going to see at different x's, what is the sign, and by sign I mean a positive or a negative sign. This is called a sign chart. And we're going to start by putting our zeros in. We start with our lowest one, which is the 0 most to the left. When x is negative 7, this value will be 0. When x is 2, this value will be 0, and we leave spaces in between. The reason is these are the places where it could be crossing 0. And so we're going to pick any number less than negative 7. So like negative 8 is going to be a test point. And it's easiest to plug it into the factored form, although we could have plugged it into the original form as well. And we're going to look at the sign. Negative 8 plus 7 is negative 1. And we don't care as much about the negative 1 as much as we just care that it's negative. Negative 7 minus 2 is negative 9. That's a negative as well. A negative times a negative is a positive. And what we'll see is any number less than a negative 7 will give us a negative times a negative, which will give us a positive. Any number between negative 7 and negative 2 will also give us the same answer. And in this case, we can pick, I don't know, like zeros between negative 7 and negative 2. 0 plus 7 is positive 7, which is a positive. 0 minus 2 is negative 2, which is a negative. And a positive times a negative is a negative. And so all numbers between negative 7 and 2 will give us a positive times a negative. And when we cross over 0 again, check a number like 4. This will represent all the numbers greater than 2. We'll get a positive times a positive, which is a positive. Now, often it switches, but sometimes it doesn't. You need to actually check these to make sure the sign switches, because sometimes it doesn't. And so now what we're looking for is, where is this above 0? It's above 0 when the values are positive. And so the solutions will be x is less than negative 7, or x could be greater than 2. Because if x is less than negative 7, we'll get a negative times a negative, which was a positive. And if x is greater than 2, we will get a positive times a positive, which will give us a positive. And this is our technique for making a sign chart. We put our zeros in, and then we do a test point in each section in between them. to see where they're true. Notice that because it was greater than 0, we can't use the endpoint. If this had been greater than or equal to 0, then 0 would also be a solution. When x equaled -7, that would also work. I hope this helps. This is kind of a tricky thing.